Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. One of the themes of homological algebra is that if you want to study a module, you should substitute it with its free resolution, which records how it is built from the simpler free modules. And if you want to use this though, you have to realize that, well, you can construct this free resolution in lots of different ways. So another theme of homological algebra is that what remains invariant, it doesn't matter how you try to construct it or form this free resolution, those properties are things which are important to the module and give you actually invariance of the module. So to make this work, I want to pose the following question, which hopefully makes this idea a little bit more precise. And that is, can you understand or study the category of R modules using the free resolution of modules? And to give a little example, it's a simple motivational example. Let's have a look at the following situation, which I want to describe now. Okay, so here we want to look at just some abelian groups, in other words, Z modules. And here we have one, a cyclic group of order 6, Z mod 6Z, and he's a Z mod 2Z. Okay, and when you want to study a category, you want to study morphisms between the objects. Okay, so here we have a very, very simple morphism, which is essentially given by multiplication by 3. In other words, the coset of 1 goes to coset of 3 here. Okay, that's great. Now for each of these modules, remember you can take a free resolution. Okay, so in this case here, what's the free resolution of this? Well, you can take the surjection of Z onto this, and the kernel is 6Z, so that kernel is isomorphic to Z, so you can also write an exact sequence of this form. So Z goes to Z by multiplication by 6. Okay, so the image here is precisely the kernel of this map, and so you get a free resolution here, and you can just pad it out with zeros towards the end if you want. Similarly here, you get a free resolution of Z mod 2Z. Okay, so Z surjects onto here, and the kernel is 2Z, so I'll write it by putting a Z here, and if you multiply that by 2, that surjects onto the kernel of this map here. Of course, this is injective, so if you put a 0 here, you'll get this exactness at this point here, and again, you'll get a free resolution of this group here. So the idea is we want to replace these two modules with these free resolutions, this blue part here, and say, well, how can you study this morphism? Okay, so I guess what would be the ideal situation is if we have a morphism over on these chain complex side. And in fact, that's what we'll get. And the easiest way to do that would be to say, well, let's just multiply by 3 in the same way here, okay? That will get your answer. So let's just see what happens. So I guess what you want to do is, let's suppose that 1 gets mapped to 3. If 1 gets mapped to 3 here, let's just check that this square commutes. Okay, so 1 will go to the coset of 1, and that will go to the coset of 3 inside here. Okay, and here, if you go to 3 here, this will go to the coset of 3, so this commutes. And in fact, since this is surjective, once you say where this goes to here, okay, this morphism is fixed. Okay, so there's only one possible morphism here, such that this square commutes if you fix this map, which is a multiplication by 3 map. Of course, you want a morphism of the whole free resolution. So how do we get that? We also need a morphism here, which makes that commute. And how do we do that? Well, if you go around the square like this, you multiply by 6 and then 3, that's 18. And so you want to go around here, put a morphism in here, which has to be multiplication by some integer, such that when you go around like this, you also get multiplication by 18. Now this is 2, so I guess what you have to do is you multiply by 9 here. Okay, so that's very well and good, and it shows you that, well, in this example, we can recover this morphism by looking at this morphism of the free resolutions, and it's also actually true that we can recover this morphism here, because how do we recover this group from the free resolution? We can look at the homology of this complex H0. Okay, so if you forget that and you replace it with zeros here, the H0 of this free resolution gives you this, And then if you take h0 of this, you will in fact get that. But what you might notice is that actually this wasn't the only choice for what you can do. Okay, so instead of sending 1 to 3, remember 3 plus 2z just means all the the coset of odd integers. So actually you could have just said 1 to 1. That would also have worked. You could also send that to 1. And in that case there, when you go around this way, okay, you've multiplied by 6, and then you've just do the identity here. So that's multiplication by 6. And if you want to multiply by 6 going around this way, I guess since you multiply by 2, you better multiply just by 3 here. But still, you can do it. But what you'll find is that here you have different morphisms of the free resolutions, which give you the same morphism here. And so you'll find that there are more morphisms on the free resolution side. And so the question is, well, how can we sort of like record the fact that when you look on this side, you only have one morphism? And that's where the notion of homotopy comes in, and that's the subject of this video. Okay, so let's define what is a homotopy. Okay, so suppose now you have two chain maps. So here we've got essentially two chain maps, the blue ones on the free resolution and the purple ones. Okay, suppose we've got a purple F dot and a G dot, and that goes from a chain complex C dot to C prime dot. Okay, so that let's visualize what goes on here. So here we have the C dot, our complex here, and we have C prime dot, which is our complex here. And we have two chain maps. So the F dot will consist of the purple vertical downward arrows, and the G dot will be the black vertical arrows here. So we have two of them. And what does it mean for these to be homotopic? It means they're homotopic if their difference is of a very, very special form that's given by certain morphisms which go SI, which go from CI to CI plus 1 prime. Okay, so let's just see where these are. So the key point is that these will go from, SI will go from CI to C prime I plus 1. So it will go down and to the left. So that's where SI goes. And then SI minus 1 will start from CI minus 1. It will go down and to the left like that. Now Fi minus Gi are maps from Ci to Ci prime. So they're maps this way. And what we basically want to say is that if the difference is of the form where there exist these diagonally backwards maps Si, such that the difference is equal to the sum of going around this way and going around this way. So going around this way this is Si, and this is the boundary here, the prime boundary at stage I plus 1, degree I plus 1. And going around this way is going to be, you apply this boundary I first, and then you apply this map here, which is Si minus 1. Now these maps, these blue diagonal maps here, they're called a homotopy if this occurs. And why is this called a homotopy? So let's just see why we have this definition here. So what's the difference between, well, sending 1 to 3 or 1 to 1 here, okay? Why could I have done either of these two things? And that's because when you look inside here, 3 and 1 are the same. And why are they the same? Well, basically, to be the same, since this is exact, it means they differ by a boundary. So that means something in here. So that means that really the difference comes from a map from this down to here. There's your downward backwards arrow. So now all we're insisting is that we have a lot of these downward backward arrows such that they give you, when you have the difference of two maps are given by this formula here. Okay. So this is the proposition which sort of captures the phenomenon that you see here. Why are there two different maps, the blue one and the purple one, that give you the same thing? More generally, if you have homotopic chain maps, okay, such as perhaps we've got in this setup here. Of course, when we have a chain map, remember it induces a map on homology. So hi of f dot will go from the homology, ith homology of c dot to the ith homology of c prime dot. And the same is true of hi of g dot. Well, if they're homotopic, then these two are actually the same. So in this example here, basically, this map here can be given by h0 of either the blue or the purple. And this actually will give you a homotopy. Of course, this homotopy here is going to be 0, or the other ones are 0. And so that's going to show you why this gives you the same map in this case. Okay, so the proof of this is very simple, and it also partly demystify where this condition comes from. Okay, but the simplest example is what I've said here. Okay, so you just look at this and you see that, well, you know, there's a lot of choice in where you map to here, and the choice is given by, well, you have to go back to boundary. Okay, so let's apply this to both sides of an element inside here. Okay, so there's our HIF dot. And what are the elements of this? So remember, it's basically cycles modulo boundaries. So you take an element in here, which is a cycle, so it goes to 0 under this map. And you look at the coset corresponding to the image of this. So remember, everything in the image of this is inside the kernel of that, because the composition of these two is 0. Okay, so we have a cycle Z, which is inside the kernel of this map here. And you look at the corresponding coset, so the coset of the boundaries, boundary I. And how does this homology functor work? Okay, so you just apply Fi to the Z, Fi to the Z, and look at the corresponding class downstairs. So Fi of Z is now down here, and you look at the coset corresponding to the boundary, but that's the image of this map here. So this Bi is different from that Bi. Now you use this condition here to rewrite what Fi is. It's going to be Gi plus what's over here. So you've got Gi of Z, plus you've got this applied to Z, so that's boundary prime I plus 1 composed with Si of Z, plus this last bit here, which is Si minus 1 composed with boundary, Si minus 1 composed with boundary I of Z, and you look at the coset of that, so that's plus Bi. Okay, so what do we want? Well, we want it to be equal to Hij dot applied to this coset, that homology element. So that basically means that we want all of this to disappear. Now the first thing is that Z is a cycle, so this is actually equal to 0. So that's going to be 0. The next thing is that this here, so that also tells you partly why, oh, okay, you can look at adding this term here, because when you apply the boundary, it's going to be 0 anyway. What about this one here? Well, this is the boundary of something. So you've just added in a boundary, so it'll get absorbed into here. It's not going to change the coset here. So you, at the end of the day, you just get Gi of Z plus Bi, and that's, of course, the action of the homology, ith homology of this G dot on that homology element, this coset of that cycle Z. And there you have this proposition. So the key point is that homotopic elements, okay, homotopic chain maps induce the same functor on homology. Okay, so we're going to use various properties of being homotopic. Okay, I won't prove them, but they're proved in the same way as what goes on here. Okay, and that's going to tell us an answer to this question eventually. Okay, so the first one is that being homotopic is an equivalence relation. And in fact, it's more than that. We can look at firstly the homomorphisms, the chain homomorphisms from C dot to C prime dot, these chain maps, and this is an abelian group. And in fact, the equivalence class bracket F dot of F dot is just a particular coset of this with respect to this a subgroup. And what's that subgroup? It's the subgroup consisting of all chain maps, okay, inside here, which are homotopic to 0. So remember, of course, if you put zeros in here, all the squares will commute. You'll always get 0, doesn't matter which way you go around. Okay, so you've always got the 0 chain map between two things. Okay, that's also part of the fact that this is an abelian group. Okay, and so the ones which are homotopically trivial, in other words, homotopy to 0, okay, that forms a subgroup. Okay, and of course, if they differ by that subgroup, so basically they're all the elements of this form for some homotopy SI. Okay, all the things of this form for some homotopy SI. And if you look at all of those, that forms a subgroup. And of course, differing by something in that subgroup means that they're homotopic. Okay, so that's the first thing. Okay, so you have an equivalence relation on chain maps. And so the key point is that, yeah, if they're equivalent, okay, then they induce the same thing on homology. The next thing is that this equivalence is rather nice, okay? It respects composition. So if you have homotopic F and G as you have here, what you might want to do is you might want to post-compose this with another chain map, right? And ask, well, if you post-compose, so suppose you compose with some chain map H dot after the F dot and the G dot, are they still homotopic? And the answer is yes. What happens if you pre-compose? You have another chain map from here to this C. Let's call it H dot as well. Okay, then if you pre-compose homotopic chain maps with some chain map, then still they're going to be homotopic. Okay. And so that allows us actually to do something that's really interesting, and that's to form what's called the quotient homotopy category. Okay, so I'll denote it with this color graphic K here, and often it's given by the symbol K of the category mod R. And what we have here is, again, we're just looking at chain complexes, but we're going to change the Hom sets a little bit. So the Hom sets between two chain complexes C dot and C prime dot. Okay, we're going to start with this abelian group, which is the chain maps between C dot to C prime dot, but we're going to only look at equivalence classes with respect to homotopy. So in other words, we're going to go mod out this by this subgroup I C dot C prime dot of chain maps which are homotopic to 0. Okay, so this is the these Hom sets. Now, if we want a category, okay, we need to be able to compose elements inside here. Okay, so what happens if you try to compose two equivalence classes? What's the definition of that? Okay, so and when can you compose them? Of course, when you can compose them, just means that this F dot and G dot are composable as chain maps. Okay, and what we'll do is we'll define this composite to be just the equivalence class of F dot composed with G dot. And of course, the thing that you have to check is that this is indeed well defined. In other words, if you replace this F dot with something homotopic to it, okay, does this stay the same? And that holds because of property 2 here. So that's why I mentioned this, so that you do actually get a new category. And you can check the other category axioms hold here. And the key point is that what does the remark allow us to do? The remark allows us to do the following thing. We now have a functor. Before we had a functor from chain complexes to abelian groups. That's the ith homology functor. It actually gives us a functor from this category K, this homotopy category, to abelian groups. And that's because, well, how do I apply this functor? Well, we know what it does, this HI does on chain complexes, on objects. You also need to know what it does on morphisms. And what it does on morphisms, and what are the morphisms? They're things like this, equivalence classes like this. Now we know what HI of an F dot is, but what about the equivalence class? Well, even if you change this to anything that's a homotopy equivalent to it, you get the same HI. So you just pick HI of anything in that equivalence class. They all have the same value, and that's going to be your functor there. Okay, so let's answer our original question. Okay, so I'll give you an answer. I won't prove why this is true, but I'll say some words about that, the proof of this in a later video. Okay, so remember what we're trying to do. We're trying to replace a module with its free resolution, thinking that in some ways that's easier because it's made from free modules, which are simpler objects. Okay, so we're trying to think of this free resolution as we take a module and we're going to construct it from simpler building blocks. Okay, so there's our free resolution here. Now, one way we can write this out that's a lot more succinct is as follows. Firstly, the free resolution itself is just the free part. And what do I mean by the free part? I'll denote it with an F dot. So I'll have, from this F0 to the left, it's going to be the same. And then I'm going to replace it with zeros. Okay, so that's also sometimes referred to as the free resolution. Okay, this F dot here. Okay. And how do we recover the M from this free resolution? Remember, we can look at H0 of this will be M, and all the other homologies will be 0. Okay, so that's what you have here. Okay, that's great. And then the new way we're going to write this out is that, well, we can also consider this m itself as a complex. Okay, so what complex is that? So we need a sequence of R linear maps. Okay, so we're going to put m in degree 0 and zeros everywhere else. And since there are zeros everywhere else, the only possible maps that you can have here are zeros. Note that this is now a complex. The composition of any two maps is going to be 0, mainly because you always have to at least start or finish with a 0. And most of the time you'll both start and finish with a 0. But there's only one non-zero value, so that has to be the case that at least when you compose two boundary maps, okay, either the beginning or the end will be 0, so the map is 0. What's the homology of this complex? Of course, the homology recovers this m in degree 0. This is the only place where you have homology, because everywhere else it's a subquotient of 0, which has to be 0. Here, the kernel of this map is going to be m. The image of this map is 0, so m mod 0 is the 0th homology, which is m. And the other thing that you have here is, of course, well, you've got a map from f0 to m here, and actually you have a chain map. Okay, the only possibility is to put the zeros everywhere else. And if you want to check that this is indeed a chain map, you should check that all the squares commute. Most of the time, you're just comparing two maps to 0. The only time you don't compare two maps to 0 is when you go around like this and when you go around like this. Okay, this is 0, and this one you have to check is 0, and that's because, well, this f1 maps to the kernel of this map here, so that goes to 0 when you go down here. Okay, so this is actually a chain map from this f dot to the complex associated to m. So often we just denote it by m as well, but this is the complex, basically the module thought of as a complex. Okay, so now that's just looking at one module. Suppose we have two modules like we do here, and we want to look at the homomorphisms between them. So let's suppose we have another n, and we want to think about some free resolution for that. Replace it with this g dot. G dot maps to n. Okay, and then the question is, well, how do you understand the R module homomorphisms from m to n using just the free resolutions f dot and g dot? And the answer is just very simple. Okay, what you do is you look at the homotopy equivalence classes of maps from f dot to g dot. In other words, inside this category K, you look at the homomorphisms from f dot to g dot. And what is that isomorphism? How is that given? Well, you take this f dot, or rather its equivalence class, okay, and then you take a chain map or an equivalence class of chain maps, okay, and then you just look at h0 of that. And since h0 of f dot and g dot are m and n, you'll get a homomorphism from m to n, and this is going to be this map here is going to give you a bijection. And that shows you how you can study this category of R modules just by looking at their free resolutions. And this turns out to be a very, very important theme in homological algebra. I hope you enjoyed this adventure in pure mathematics.